Okay, great. So it's our pleasure this week to welcome Wolfram Barfuss from the Tübingen AI Center and also the Potsdam Institute for something and Princeton University to speak about collective learning dynamics. Please go ahead.
Thank you very much for the invitation and the opportunity to speak here. Yeah, I will talk about collective learning dynamics, but before we get into what that actually is or what I mean by that, let's first address the question why this is interesting. So when the future is uncertain, the environment is complex, or other agents are changing as well, pre-programmed behavior cannot work, and so we need a multi-agent learning approach. And for example, you can think of mobility system, swarm robotics, or in a broad sense, also the provision of public infrastructure. But also when we think of machine learning that is applied in the world, I would argue multi-agent learning approach makes a lot of sense. So traditionally in machine learning, we have a lot of data. We use that data to train a more and more complex model these days, and then can use the model to create predictions and recommendations that we can act upon. And when we act upon those decisions in the real world, then often this changes the data the model has been trained upon, and this creates a feedback loop, which is important to consider to not violate assumptions that went into the scheme. And to give you some examples that are more or less relevant in this regard, you can think of web translation, where machines learned to translate between languages, and then users like to build websites with the translated text, which then enters the web, which is often used as a data set to learn the translation in the first place. It's also the case for traffic navigation, where we get real-time recommendations based on the current situation of the traffic. It might also occur in commerce and trading, and perhaps also more relevant with regard to fairness, who or who does not get admitted to a school or a college, who or who does not receive a loan from a bank, and who or who does not get out of jail early. But of course, this perspective and this framework of multi-agent learning comes with a lot of challenges. Some of those are that current methods are very slow, data inefficient, and resource and also energy intense to learn, to train, and then to act. They're often difficult to reproduce and also hard to interpret. When we are in a multi-agent learning setting, then we might also have the occurrences or get into situations known as social dilemmas, where it is not so clear or not that obvious what we should do in those situations. And often in the real world, we have to deal with observational noise and uncertainty, and that makes the learning process fragile. Which brings me to the agenda for this talk. So first, I'd like to introduce you to this approach, what I called collective learning dynamics, addressing part of the first challenge points here. Then we look into cooperation in social dilemmas, and we can look at that from the angle of cooperative AI. Last, I will address some recent work regarding environmental and observational uncertainty. So let's get right into collective learning dynamics. And the basic algorithm or basic learning process that we are considering here is called reinforcement learning, where in a multi-agent setting, we have a couple of agents, and an environment. The agents can choose between, choose each from their action set and choose a joint action based on their current policy, which is kind of a conditional probability distribution, choosing those actions. Then based on those choices, the environment may change probabilistically, and the agents observe the new state of the environment and also receive a reward signal. And so the policy is typically conditioned on what they observe, and then a probability distribution over the actions. Now, the essence of reinforcement learning is basically that during this interaction, the agents compute or assess their current so-called temporal difference error, which tells the agents how to adapt. And this process of temporal difference error is occurs both in natural and in artificial agents. So it was developed as a technical machine learning method, but then also discovered in the brain, where dopamine signal has great similarities with this technical method. And then based on this temporal difference error, the agents can adapt their policy in order to improve it to get more reward over time. That is the kind of the goal of this reinforcement learning agents. Now, to kind of make sense of this a little bit more, I found the concept of cognitive levels of analysis very helpful. So this dates back to David Marr's levels of analysis, and says basically that it is valid, fruitful, and even necessary to analyze cognition by forming different abstraction barriers. And the one they proposed was a computational level, which is the abstract characterization of the computational problem that is being solved. An algorithmic level, which is basically the algorithm executing a solution, and then an implementation level, kind of the hardware that is implementing that algorithm. Now, if we apply that now to multi-agent learning, let's first recognize that we, for now, do not deal with the implementation level. So we're only concerned with computational and algorithmic level. Now, for a computational level, in multi-agent learning, we typically have a game theoretic setting, and with an environment, it's called a stochastic game, where the environment changes based on what the agents have chosen, and kind of a solution that is typically desired in such situation is a game equilibrium. And of course, there are multiple game equilibria out there, but that's kind of what a multi-agent learning setting might want to put forward as the computational problem that they're trying to solve. Now, as I said, the algorithm that we are looking at is called temporal difference reinforcement learning. And kind of most work is done on the concrete process models, really learning algorithms that try to deal with noisy environments and learn better in these situations. Now, to motivate this approach of collective learning dynamics, let's ask the question: what if we could construct an idealized process model of learning dynamics that sits in between the game equilibrium, the computational level, and more concrete process learning algorithm that would be interpretable, deterministically reproducible, and also implemented fast, and then relate this learning dynamics level to the adjacent levels. And this is basically the kind of the conceptual motivation for this collective learning dynamics approach. It is based on the analogy between evolutionary game theory and reinforcement learning. And the existing work in that domain, broadly understood, tends to focus on more simple learning algorithms that, for example, are not capable of dealing with a changing environment. So the goal is to advance this approach and understand the dynamics of collective learning in changing environments as a dynamical system. And the basic idea how to do that is to start from really standard, stochastic, independent, so-called model-free reinforcement learning algorithms, for example, like Q-learning, but there are others as well, and really use those standard algorithms and then perform a mathematical separation of timescales between the interaction process and the adaptation process. So you can imagine to have infinitely many times of interaction between two processes of adaptation. And this allows us then to formulate and write the reinforcement learning process as deterministic, environmental aware, now that is kind of the contribution here, reinforcement learning set of equations. And the basic structure of those equations are that the new policy equals the old policy times the exponent of the policy average temporal difference error times some learning hyperparameters, and then properly normalize that. We have a probability distribution here again. There's a question I see. Should we? Yeah, why? I mean, yes. I'm happy to have questions. Yeah, please.
Yeah, Corentin, go ahead.
Yeah, okay, thank you. I was wondering, this makes me think a little bit about aging in materials. This fact that you have a fast time scale and then like a slow time scale that in which a system changes its nature essentially. So is there also an analogy or some connections between what you present here, the reinforcement learning equations, and what people use to describe aging?
I haven't thought about aging, especially with the separation of timescales. I have thought a little bit about the aging of agents, and if it makes sense to think about that agents can die and what this means for a learning process with respect to the discount factor, to which we come at a moment. No, I think we need to take that later in a more, I would need to ask something back, more details about the aging. I don't know, I'm open. We can discuss it now as well.
No, I mean, I don't do aging myself, but as I understand it, it occurs in systems that have a very complex, very rough energy landscapes. And when the system, you have the dynamics of, let's say, when your local minimum, that is a fast dynamics. But then what occurs over time is that you go to, for instance, an energy minimum that is lower and lower in this complex energy landscape, right? So
okay.
So it's a bit like an optimization problem, if you wish, but where it takes it's a very inefficient one, where it takes a long time to actually find, or you never find a global minimum, but it takes a long time to actually drip down reach a lower and lower minimum, basically. So that's how my understanding of it. Yeah.
So the processes of aging would be the slow process where they don't change drastically, and then basically the almost jumps to new minima.
Yeah, or find us maybe a very unlikely path to go from one.
Okay.
Yeah.
I mean, it is definitely related to optimization, and one could think of this stochastic version of reinforcement learning, kind of a stochastic gradient descent process, whereas this deterministic would be kind of a standard full gradient descent method. and it has, I think it has more to do with getting rid of the noise in the optimization process. All right.
Thank you.
Cool. Yeah, I continue, and maybe we can come back to this later. All right. So far from the theory side, to give you an idea of what is happening, let's look at an example. And we look here just for the sake of having an example at an example that was examined in the previous literature, zero-sum games with changing roles. And to make it more concrete, think of penalty kicks where kicker and keeper agent, or basically the agents change roles between kicker and keeper after some condition has met, and both have to choose either the left or the right side. And of course, if the kicker chooses left, but the keeper right, then the kicker scores. And if they choose the same, then the keeper scores a point. Now we can use those deterministic learning dynamics to plot a projection or multiple projections of this policy space, where these errors are basically the temporal difference error, which show the emergent learning dynamics, and also plot, of course, individual learning trajectories. So here, for example, we have on the x-axis the probability of agent 1 to play the left action, and on the left plot for state 1, and on the right plot in state 2. So now the states encode who is the kicker and who is the keeper. So here, for example, the agent 1 is the kicker and agent 2 is the keeper, and here it's the other way around. But it's not too important here, because you see that the dynamics are circling in basically in a qualitative similar way in both states. So and just to mention that on the y-axis we have the probability of agent 2 to choose left in state 1 in state 2. Now, to relate those dynamics to more lower level process algorithms and really understand how they connect to a lower level concrete process algorithm, I thought about a sample batch algorithm that introduces a batch of stored experiences of, you can think of memory of some size k, and also needs to do a value estimation separately, which is a part in the reinforcement learning algorithm. So it has these two additions to the most standard reinforcement learning algorithm. And now we can compare this concrete process model algorithm with the dynamics. And for a batch size of 50, you see that both do not match too well. So that you see how the algorithm is still very stochastic, and it's really hard to relate them to each other. But if we increase the batch size sufficiently, then this match becomes increasingly close, almost perfect, I would say. And we can also look at the different terms of the temporal difference error. And so here in green, we see the temporal difference error over an increasing batch size. And here, the relative error between the batch algorithm and the deterministic dynamics. And you see that they become sufficiently close that the effective learning trajectories up here sufficiently similar. Also interesting to note here that there are two processes of convergence going on. So for the red and the blue line being basically the reward model and the environmental dynamics, the transition model, they go much faster than those terms that have to do with the value estimation inside the learning. And this, I think, is an interesting avenue for future work to understand this process even better. But for now, let's summarize that this separation of timescales can also be understood as learning with an infinite batch limit. And since an infinite batch limit is actually conceptually very similar to having a perfect model of the environment, we can also interpret these learning dynamics as if the agents have a perfect model of the environment and also the other agents' current policy. So in a nutshell, whereas the standard process reinforcement learning algorithms have to find a signal within the noise, these reinforcement learning equations, the dynamical systems point of view, just uses the signal. And as a benefit, we have a quite interpretable, also reproducible because it's deterministic, relatively well implemented, I would say, so fast tool, which is also cognitive plausible and a dynamic approach to collective situations in changing environments. The limitation, so you could say, well, it is limited to somewhat stylized models that are made to understand something, not to let loose to really large scale optimization procedures. There it won't work, it can't work. That is not what it's designed to do. So let's apply them and apply them in the domain of cooperation and social dilemmas. And if we mix that with artificial intelligence, we get cooperative AI. Here a comment that was put forward. And it says that to help humanity solve the fundamental problems of cooperation, we need to reconceive artificial intelligence as deeply social. And what I will focus on is the situation of cooperation in changing environment. And surely a fundamental problem of cooperation is the climate crisis. So here you see the temperature anomaly over the last 22,000 years. And you can see in this graph that in only 50 years, we tipped from the 10,000 years of the Holocene into what people call the Anthropocene, the age of humans, where we have as humanity a relevant impact on the global scale. Now, Earth system models tell us what we do the next 50 years will determine the next 10,000 years. So it's really a critical time to live in. And we can ask now, what makes intelligent adaptive agents inherently cooperative and sustainable? So, or in other words, what kind of intelligence is needed to solve such a problem? And the particular aspect I'd like to focus on is that often in current models of collective action under some threats, we don't have a time component in them, or a future, or not even an environment. So we can't really ask the question, what role does environment, time, and future play here? So really in a dual sense of the meaning, we don't have time. So this is the motivation why we constructed this model, to assess what caring for the future can do in such a collective action problem. And we started out by taking a classic public goods game, also known as a prisoner's dilemma if we have only two agents, and situated that in a prosperous state, in a state of the environment. So now let's first look at the game at this environmental state. Now the nature of such a dilemma is that imagine we are agent 2 and agent 1 would cooperate. Then we can also cooperate or defect, but defection would be better for us in this case. So we should go for defect. If agent 1 defects, then we should also defect, because 0 is better than -2. Since the game is symmetric, this is true also for agent 1. So regardless of what others are doing, we end up defecting. Whereas the dilemma is that we would gain more reward if we were both cooperating. So that's the story of why we call that a social dilemma. But now we said, okay, defection might not be only socially suboptimal. It might also trigger a collapse, or just increases the probability of collapse to collapse the environment into a degraded state. We just assumed, okay, here agents have to suffer with a negative collapse impact M, and only after some time, depending on a recovery probability, they can recover into the prosperous state. So this is our kind of embedded, environmentally embedded public goods problem. Now we can analyze that using some analytical calculations and look at the parameter space of this model here, spanned by the collapse impact M on the y-axis and the caring for the future parameter gamma on the x-axis. And you already see kind of 3 regimes in this parameter plot. And maybe I should mention what the discount factor does. It's, I mean, of course, those of you who are familiar with discounting, it's a discount factor, but essentially a discount factor caring for the future parameter gamma of 1 means that the agents care as much for the future as for the present, and values lower than 1 means that they kind of discount the future with exactly that value. So the next times that would only be times that discount factor valuable. All right. So if we are above this blue line, then we are at the tragedy regime, so the famous tragedy of the commons, where in a learning dynamics picture from all areas of the policy space, agents learn to go to the defective point, so to mutual defection. So this is when the collapse impact is not so severe or the caring for the future is not too high. If we cross this blue line, then we enter a so-called coordination regime, where in the learning picture, it now depends where the agents start, whether they go to mutual defection or to mutual cooperation here in the upper right. But interestingly here in this model, it's also possible to cross this green line. And when we cross the green line, then we are in what we call a comedy regime. And the comedy regime is special in that sense that regardless of what the others are doing, agents always want to cooperate and always learn also to cooperate from all points in the policy space to mutual defection. And the interesting point here, if we have a sufficiently severe collapse impact, then it is caring for the future alone, which can transform the tragedy of the commons into a comedy. And this is true assuming no social reciprocity whatsoever. So the agents are basically completely ignoring other agents and only reacting to the environment. And this is just to say that in typical models or other modes to ensure cooperation are based on some form of social reciprocity. but you can imagine on a global level, this might not always be possible to create. And from a methodological point of view, you see that these analytical predictions basically fit well to this learning dynamics picture, which is also nice from a methodological point of view. Now you might say, okay, this is perhaps interesting, but does it also scale to more complex environments? Because this is still very simple. So we also used a deep reinforcement learning approach for discovering sustainable policies in a slightly more complex environment. And here the agent even is able to stay within some desirable regime of this state space. And also other works on a multi-agent domain have shown that deep reinforcement learning can solve a collective harvesting problem. So this is so far quite nice, but of course in the real world we always have uncertainty to deal with. So agents have to be have to be able to react to an uncertain environment and not knowing exactly what's going on. So in the next part, I will kind of refine those learning dynamics to be able to deal with irreducible environmental uncertainty, because so far we assumed that agents observed the environmental states perfectly. As I said, often in the real world, the observations are noisy and some parts of the world may be fundamentally unobservable. And from a theoretical point of view, this is considered harmful. We should expect that learning cannot perform as well as compared to an agent that is capable to observe the true state of the environment. Now, to deal with this problem constructively, let's model this partial observability in the agent environment interface. So this is actually very similar as the picture we have seen before, but now instead of observing the true state of the environment, agents observe a can think of set of observations which are a conditional probability distribution based on the states. So we have an additional kind of data structure, additions to the dynamics of the environment and the rewards. Here, the kind of observation function that is included in this model. Now, this makes other methods of some formal type increasingly limited, because the kind of the generality of the setting is more general, of course, than if we assume they can observe the state perfectly. And so here our approach is really a kind of a naive one. We just say, how would agents learn that treat observations as if they were states? And what would this mean for the dynamics? And if we carry out this separation of timescale procedure, then it turns out that the agents actually infer the true environmental states in a base optimal way. And they do that through that infinite memory limit. All right, so far to the technicalities. Just I am deliberately short on that. Details are in the paper, or happy to provide them to you later. Let's now see what positive effects partial observability can have. So for one, it can stabilize the learning process. So here we are back at our zero-sum competition. And if we look at that under some agent hyperparameter values with no observational noise, then we can almost chaotic learning behavior. So some form of periodic orbits close to chaos. Now, if we assume that the agents become less and less sure in what state they're in, so that would mean they are less and less sure whether they are the clicker agent or the keeper agent. So you see, it's a quite abstract example, but perhaps the agents get drunk. Then we see with 25% noise, the learning is still chaotic in the policy space, but you see it already dampened in the reward trajectory. And if they completely lost track who they are, then the reward stabilizes very fast, goes to a 0. So that's kind of the optimal reward you can achieve. And in the policy space, we have a kind of separation of timescales on the circling, and then a slow time scale going from here to the center of the policy space. But that has no effect on this reward. So this should have come earlier. But anyway, now so much to the stabilization process. It can also, partial observability can also transform social dilemmas in a situation where agents are not sure whether they are in a tragedy of the commons, in a prisoner's dilemma, or in a coordination regime, also known as a stack hunt game. And here there's also a observational noise parameter that we can tune, which makes the agents less sure or less aware whether they are in the prisoner's dilemma state or the stack hunt state. Now, if we look at the variation of the noise level on the x-axis and the average reward on the y-axis, then here both agents on top of each other make this purple line. So there's complete equality. When there's no noise, they start with an average reward of about 2.5, which slightly decreases with more noise. But then we see a bifurcation where agents are able to obtain this high rewarding 5-point reward. They also go more to 0 reward, but this 5-point reward is supported as an equilibrium in the policy space. And if we look at the times it takes to converge, we can nicely see this critical slowing down before this kind of phase transition here. Okay, this kind of nice effect of transforming social dilemmas is only true under homogeneous uncertainty. If we assume that agent 1 is fully able to observe the true state, and only agent 2 is not clear of what's going on, then we see a different picture. We see inequality emerging. So agent 1 is able to exploit agent 2, but we also see kind of this critical slowing down before a bifurcation. And interestingly, the type of bifurcation seems also different. Here more continuous, here more discontinuous. All right, so now the last point I want to make is that even a single agent can learn better outcomes faster. So now this is perhaps the most complex environment we are going to look at. So let's see if I can explain it in some meaningful way. So here we are looking at a renewable resource. And the challenge for us is that we want to have a discrete environment. We want to have a discrete set of states. So let's imagine we take a renewable resource with a capacity 5, so a logistic resource growth function. And then we just discretize the resource state space into the discrete natural numbers. And then I basically assumed, let's give the agent 3 actions: a harvest a lot action, a harvest a little action, and harvest nothing. Now, what is a lot and what is little depends on the maximum resource regrowth rate that occurs on one of the discrete states. Now, let's assume that the resource is at state 3. The agent harvests, which decreases kind of the state. Then we let the resource regrow according to its continuous regrowth function. And then it would regrow to a number between 2 and 3. And in order to discretize it, I use a basically probabilistic discretization method, just a normal distribution, and then the area under this distribution corresponding to one of those states is the transition probability for this state action combination. So much to the environment. Now, main point is we want to look at some observation. And so far we've looked at noise. Now let's look at a situation where the agent is not capable to observe the full state space of the environment. And here we look at all functions, all observation functions that treat single or adjacent states as one observation. So the most complex, so we can then also induce some kind of a complexity ordering on those observations. And we say, okay, the most complex observation would be the one where the agent observes the true states of the environment, each as a single observation. A slightly less complex would be where these two adjacent observations appear as one observations and the other states as single observations. And those two states would move all around all adjacent states. We can have, of course, then 2 adjacent states and so on until we get to very simple or less complex observations, until the final the most simple observation, the agent just observes all states as one, or in other words, it doesn't observe any states and can't react to those states. Okay, that's the environment and the observation function. And now the task is to look at the outcome of all these possible observation functions. And first, let's look at the speed outperformance. So with that, I mean observations that perform better compared to the fully observable agent. So here, for an environment with a capacity of 6, so 6 environmental states, we see here on top all the dots corresponding to a single observation that perform better compared to this fully observable agent. And you see that's quite some. It's not so hard to get to faster convergence than the fully observable agents. And these 3 dashes on top are kind of the most successful, the speediest observation functions. And you see some similarities between those. So here there's always a separation between this lower half and this upper half. Now, the reward outperformance here with this environment of 6 is less common. In fact, here only one observation, this observation function, performed better compared to the fully observational agent. And you can also see that these dots here, which are ordered according to this complexity, appear that very simple observations perform very bad. So they are much worse than the agent with the perfect observation. And the one that performs better is of intermediate complexity. Now, if we combine reward outperformance with speed outperformance, we get a reward speed outperformance, a learning outcome which is obtained faster and also better. But here, only marginal one. But if we do the same analysis for environments of 7, 8, and 9 states, then we see really a consistent picture emerging. And this reward outperformance even seems to grow according or with the complexity or with the size of the environment. All right, so we noted that even a single agent can learn better outcomes faster with partial observability, which brings me to the end to conclude. So I hope I could present to you this idea of collective learning dynamics as an interpretable, deterministically reproducible, and also quite fast way to approach multi-agent learning problems in stylized environments. We applied those and saw that agents can learn to cooperate in changing environments by turning the tragedy of the commons into a comedy only through caring sufficiently for the future. And we also saw some positive effects of irreducible environmental uncertainty. They can stabilize the learning process, can transform social dilemmas to better outcomes for everyone, and also make a single agent learn better outcomes faster. And with that, I thank you very much for your attention, and I'm looking forward to the discussion.
All right, thank you very much. So do we have any questions? So I had a question with this partial observability that you show in the end. Is the idea that if I have perfect observability, then I need a lot of data to learn, even though I can treat some states in the same way, and so it's actually advantageous for me to bundle some states and say I will treat them in the same way, so I don't need to distinguish between them. Is that the sort of payoff that leads to this better performance? Or
yeah, that we can think of it as a little bit of an overfitting if we observe all states, and it is actually efficient to kind of summarize some states into observations. That is what must going on there. The question is, of course, how to find those representations, those observations in the first place. So here, this is really the brute force analysis, right. But it kind of opens the question of combining this action learning with some representation learning, which a lot of machine learning is actually about. So again, I find very inspiring potential for future work.
Yeah. Any other questions in the chat? Is that? No. Well, I had another question, and that was this whole social dilemma that you showed was with 2 agents.
Mm-hmm.
But what happens when you have more?
You mean in this work?
Yeah.
Yeah. So what we did here actually was to set up this environment, this model, with an arbitrary number of agents. So I just showed here the version with 2 agents. Why did I do that? Well, because the learning is not so easy to set up with say, let's say 100 independent agents or 200. That would require, I think, some additional mathematical machinery. I have some ideas how to do that, but here the point was to show this learning and this analytical variation in the case for 2 agents. Now, what happens with a lot of agents in we can study with this analytical approach. Basically, these critical lines in the parameter space just can be analyzed with the dependence on the number of agents. And what happens is that basically these payoffs you get in the prosperous state become irrelevant, and only this effect of collapse dominates the decisions. But of course, this is I mean, as in every model exercise, in every model, this is a consequence of how we set up this model. But yeah.
Right.
I have a question about the model as well. So presumably the 2 axes are not independent variables, right? Because you could plausibly caring for the future is like a time delay function of collapse impact somehow. Have you looked at that and how that would, in other words, people will care for the future if they see things collapsing around them. That seems
Yeah, okay.
That's what we observe in the world, right? We take no action on climate because there's insufficient collapse. So
yeah, I mean, that's
are connected with a time delay or a really imperfect.
that's a wonderful extension to the model, that how these 2 parameters could possibly be connected. We didn't examine that in detail, mainly because I think it would require additional assumptions on how this connection should be made. So we treat this gamma and this m just as independent values, and then look at the regimes. But of course, one might imagine what path in the parameter regime we would move about. So whether we first see the tragedy and then we learn to care more about the future, possibly. Another story one could make of this plot is, okay, here this collapse impact are basically results and news about the possible negative impacts of climate change. So we understand increasingly better that it's a severe problem, but that doesn't automatically translate to making people more patient, caring more about the future. So in a way, the challenge is to accept that it is a drastic problem, but at the same time be future-oriented about it, to not ignore the problem and say, I don't care, I just live in the present, live in the moment, accept the problem, and then you could be in this comedy regime.
Yeah, I understand that, but if you were to theorize a connection between the two axes, it would give you some plausible pathways through this phase space, right? You could say, well, and so I don't know whether you can get there, but it would, because simply saying we should care more for the future is great, but I'm not sure how that's going to happen. But if you can theorize a connection, at least you could see when you could cross these thresholds somehow.
Yeah.
Anyway,
Definitely.
just an idea.
Oh, cool. Yeah.
Okay, any other questions? No? Well, then we can thank Wolfram again for a lovely talk.